So the previous talks were phenomenal. They took us to the deep sea, as well as high salt concentration place, as well as the cold Antarctic. And now I'm trying to take you to the space. So I'm Venkat from JPL. Anyway, so we have done so many work based on the what are the kind of microbes associated to these rovers, or the space station, what kind of microbes are there, where in a confined situation. And more than that, can we take those microbes to our advantage and then take intentionally to the space by getting some sort of space payload so that we can have a controlled experiment up in space. So, the previous speaker was telling you about how difficult to go to the Antarctica in the Earth. I totally understand, even going down to the deep sea, which I myself went down. It is not easy. But now let me show you how we can go to the space. So I'm not able to cover all the talk here. So one of the things that what I'm going to show you here is, can we expose microbes of our interest? That means, when you think about the space, it is biggest issue is the radiation. Can the microbes that we see that is highly extremely resistant to this radiation thing, can we take it to the real space and then put it outside the space station and see how long it can survive? This is clearly why we need to do this kind of microbiology in NASA, because astrobiology. That means, if you're going to go and look for life in other planets, better don't take it with you. So that is one of the thing we call planetary protection. We have to protect all other planet all the time if you are going to look for life in in those places. But obviously, if you are going to the moon, which you already know there is no life, there's no issue. But if you are going to the Mars and beyond, yes, there may be chances of life there, or early life in there. So, but we cannot contaminate with our own thing. That's all robotic missions. But we cannot simply keep quiet, because human mission comes in place, so that microbes are our friends. So can we utilize those things for our own purpose, okay, for a sustainable living of the human in law, for a long period of time? There is a human mission. So human are walking fermenters. They carry all the microbes with them. So when you put human in equation, no chance that you are going to contaminate all the place. Let's see how it works. So this is the place that where I work. There's a couple of minutes of video. Then you tell how we actually control the microbial contamination that is going to Mars and beyond. 2 minutes video.
It's really important that we send a rover that's clean and we make sure that it doesn't contaminate Mars. My name is Mujige Stricker and I protect Mars from Earth bacteria. The next Mars rover is slated to go to Mars, collect samples so that eventually we can bring those samples back to Earth and determine for the very first time, did life exist on Mars? There's nothing that we can build that's sterile. So we take swabs and wipes of the spacecraft as it's being built. It gets put in an oven, it gets put in various chambers and clean rooms so that we can maintain that level of cleanliness. If we do find something on Mars, we have to make sure it's something that actually came from Mars and not something that hitched a ride. This is the place where the magic happens. Oh, it's definitely cool. In this lab, we look specifically at spores. So spores are those hardy microorganisms that can actually survive if it made it on the spacecraft, the journey through space, through the vacuum. It's very humbling to be a part of this big project because there are hundreds of people that have to come together and build a spacecraft. There's no one person that can say, I did this, I made this happen. It's always a we. I owe it all to Carl Sagan and watching the cosmos. I remember being a little kid, going to the public library and renting that VHS. And from that moment, the light bulb turned on. It actually was the start of my passion of science communication. We are citizens of our universe. We have to be good ambassadors when we are exploring other planets, other moons. So it's the right thing to do. It's really...
She was my postdoc, and then a student and a postdoc, and now she's a program manager for Mars Science Return mission. Anyway, so you have given a glimpse of what we are doing in our lab. So you are collecting so many different kind of microbes that are and exposed to various different things. including the space radiation conditions. So there are so many translational benefits are there, from basic science to enhancing human health in closed system, and also pathogen detection and countermeasure, because you cannot simply identify the problem, we have to come up with a solution. So we can leverage the omics data sets for medical practice. There are so many applications that I can take off from here, but I don't have time, so I'm going to do only this number three. Bacillus pumilasturi. This is a catchphrase that is space to your face. That means when you expose to this kind of microbes to the space, that will benefit to your mother earth as well, because we are doing a lot of genomics, proteomics, metabolomics, and because of those things, out of the world space to your face product development was also happen. Okay, first of all, Hank was also telling you that it cost 100,000 euros for getting one genome. Same here, $100,000 we spent to get this particular whole genome in 2,000 times period, and now you can do it in $100. And first, why do we need to do this kind of things, right? First of all, we need to see are they problematic. The answer is yes. No matter what, how much you clean, whatever it is, you will find spores in such a oligotrophic environment. That is what humanly possible that we can do, and microbes are clever than that. They know how to get into these places and all. Okay, so. But what kind of spores are the problematic? So basically, Bacillus pumilus are the one always present where whatever you do. So we got the whole genome of this particular strain because this is highly resistant to UV radiation. And also, the modern day spacecrafts are not made up of heat resistant materials. For that, we are using the some sort of chemicals to clean various surfaces. These extreme electronics are able to withstand those conditions, but it won't withstand the regular sterilization process that we normally do. Anyway, so these are also resistant to chemicals are being used, hydrogen peroxide in the surfaces, and also these UV254 radiation resistant things are also resistant to simulated Martian conditions. So these are the basic studies, worth of 10 plus years that we have done to convince NASA, hey, let us look at in space, because going to space is not an easy job because it costs money and resources. So first, UVC254, which is the known DNA breaker, double bond breaker, so that the life will not continue. And the Bacillus cetullus 168 is a biodosimetry strain, which American Public Health Association is using to sterilize the drinking water. Around 200 joules per meter square is good enough to kill everything. That's what the American Public Health Association proclaim. But some of these wild wolf, the Bacillus pumilus SF432, cannot get killed. It is only one log reduction, even at 2,000 joules per meter square. So this is one important part. Okay, then you can also simulate the Martian conditions in the lab by putting appropriate sample holders, and these individual sample holders that you are seeing there, you can put, it is 13 millimeter size, and you can put the appropriate spores in it, and then put appropriate sensors like temperature and humidity sensors to see what kind of temperature is there. Then you can also mimic to this Mars conditions and pull the vacuum out, and the Martian atmosphere is roughly 6 millibar, so you can pump in appropriate gas that is relevant to Martian conditions to keep it 6 millibar. Okay, this kind of setup, and now you can hit the xenon arc lamp, and then you can generate the 200 nanometer and above UV radiation that is normally experienced in Mars. Okay, these are the conditions that you can set up and then simulate and then expose these kind of microbes and screen what is the one that is actually surviving such conditions. Okay, so when you look into the fact, this is the dosimeter strand that which I already told, Bacillus cetullus 168 can get killed 2 minutes. So that means people may wrongly think that Martian conditions, including the UV, basically can take care of everything. You don't need to worry about life, but that is not the case. So this kind of wild wolf that we isolated from this clean rooms, actually, while assembling these Martian probes, actually survived even 30 minutes. Only 3 logs reductions, you are seeing it in even after 30 minutes. This 30 minutes is very, very crucial because when you have a lander go on land there in Mars, it actually propagate the dust. So when it comes to the dust and other things, the bugs that actually associated to the lander and the rover may get protected by those dust. Let's see about that. So I'm not having time to show that one. So it is actually higher, resistance. In other words, 1 log reduction only you will see if you have such a kind of protection. With all these things now, you can have a science payload like this. As you see, is that there are so many slots here. It is not one man stuff. It is multiple people work together with the European Space Agency and other space agency together, and then develop this kind of payload. It costs roughly $2 million. And the total science payload plus if you put everything together, roughly $5 million worth of resources you need. But before that, as I showed you, you need to show why you are going to take this kind of bacteria or fungi or whatever it is to the other outer space, right? So if you put a shield completely closed, that is called dark. That means you are not shining any UV penetrate through this. That means UV is cut off completely. And some of these things that you are seeing this actually have a Martian atmosphere, 6 millibar, which I showed you. So it's a very tightly sealed in terms of the gas leak, but it will have the Martian atmosphere, the gas. And some of them is having what 110 nanometer filter, which is magnesium chloride. So that this is called space UV. And some of the other things are actually 200 nanometer can pass through, which is supracell, and that is called Martian UV. So the one it is open, but magnesium fluoride things, it is called space U or UV space, or if it is closed like this, it is dark space. Okay, here it is tightly sealed. Martian conditions are there, so it is called Martian UV. If it is closed, this one, that is dark, dark Mars. So it left 2008, and then actually planted outside the space station. This is the European Columbus space station of the International Space Station part. This Columbus module, and here is the one that our little space payload that I just showed you is implanted by the astronaut walk, spacewalk. And here is a little bit closer look, and this is the same thing that you are seeing. So it went there in 2008 for about 18 months. We exposed outside the space station, experiencing real space conditions. Okay, and then some after 18 months, it came back to our lab, and then we were trying to do so many different things. So this bare aluminum is not actually, it's a completely polished aluminum. You can even look your face like a mirror. But when you look under this scanning electron microscope, this has pits and falls. When you have pits and falls, these kind of microbes settle in there when you prepare this monolayer. But it sits in there, and then it gives you a kind of cushion of, from the UV radiation. So after 1.5 years, we can remove all those 100% out if it is a ground control. But the one that actually taken 6 or 7 log reduction, that is clearly showing that it is reduced from the ground control for sure. So when you look at the real, I know we did so many different kind of genomic characterization and all the kind of stuff. there is no genomic changes, because these are what spores, metabolically inactive. That's why you are not seeing such a kind of genetic mutation. But actually, when you are doing, there are certain phenotypic difference. So this one is UV space 5062 variant of SAFAR 32, which we sent it out, which is the control here. Control get killed off around 2000 joules, but this is continuously moving and not get killed even 4000 joules. Is it due to mutation? I don't think so. It is some set of protein changes is happening. That's why it is phenotypically different. This is the first generation spores. Okay, and if you are looking at the vegetative cells of those first generation, this is dark space 40T5, and as I previously showed, this is 200 joules it can kill, which is vegetative cells. But this one is spores. Okay, spores 2000 joules, and vegetative cells 200 joules per meter square. But the dark space that came back from the space, it's even 900 joules, it is continuously growing. What that means, that the vegetative cells is having something that is protecting it from this radiation. That's what you want to look into the metabolites, right? So the proteomics is showing that there is a differentially regulated, either upregulated or downregulated in this particular dark space compared to the all other, including the control. So this is a very good candidate for moving to see what it is. Okay, with all the different proteomic analysis and the validation of various different analysis, it concluded that all taken together, the functional assays demonstrated that the activities of TCA cycles and energy metabolisms were decreased in space surviving strains. So that means, think about a marathon runner versus the 100-meter dash. So if you're asking Usman Bolt, he can run 100-meter, but he cannot run the marathon of 42-kilometer, right? So likewise, the sum of the bugs that is slowly metabolizing is actually surviving, but not the one that is reproducing quickly, that will die off. So with this, what we were able to get it, the metabolites are producing something different. We just saw the proteomics differentially expressed. So that is the product that NASA won't do this product. We have licensed to the private company. So they develop this space to your face thing with this kind of microbe that is exposed to the outer space. And this is called Ionia. Some of you from Greece know Ionia means eternity. This age-defying serum is commercially available right now with our space technology. Okay, so what is this actually? It helps to restore moisture to your skin and improve visible signs of aging, such as fine lines, dark spots, dullness, and wrinkles. And it is nothing but a hyaluronic acid. That any cosmetics that you have, it is there. But this space flown, bipumulus produce certain same thing, but the activity is different. It is not injurious to the human cells, and also it allows it to, show this signs of anti-aging. So this is what omics in space is doing. The issues and solutions are, from environmental omics, this can be exploited to enhance human health and well-being of the globe system. The same compound that I showed you can be used for the spacesuit to attenuate the UV. So omics in space research aims to translate findings in fundamental research to medical practice and meaningful health outcomes. The omics data sets were placed in NASA Gene Lab bioinformatics environment. So anybody who are interested, they can get into this and search for this omics data so that you can get some innovative science coming. This is not only by one person. This is the product of several postdocs and students and investigators are all over the world. Thank you very much.